Okay, welcome back, everybody. Thanks for all your good efforts on the midterms. I do believe there may be one or two questions that I need to go back and update your grades on. So if you see your grade and you're worried about one of those things that came up during the exam or even after, give me till tomorrow. I'll do an update announcement for everybody, just letting you know I got everything graded. I mean, I do have everything graded, but I think I probably need to go back and correct a few things that I had wrong on my side. So thanks for your patience on that. And yeah, hang in there, take a deep breath as we round the corner for our next half of the course. So upcoming, we have in 2 weeks again, we have our homework 5. Now we kind of, quietly left that 4 hanging out there. So remember, homework 4 is kind of a long-term assignment. You have till the end of the semester to get that in, or you can skip it. But if you skip it, then you kind of need to do all the rest of your homework. So that's kind of pick your poison. You can always come back to 4, but kind of monitor how you're doing on your general other assignments so you have at least 7 good grades. That's the goal out of our 8 homework assignments that we have for the semester. So 5 that's coming up is about symbol tables, and we'll be talking about symbol tables today. And we'll need in our next lecture to introduce what a hash table is more specifically so that you can do your assignment. So we kind of need 2 lectures, 17 and 18, before you'll have everything you need. But a lot of it revolves around linked lists. We're going to do it with doubly linked lists, which is a little kind of more intense than the singly linked list we saw in our last homework assignment. So we'll talk about where all this stuff fits in. But today we'll kind of focus on, warming up how we deal with these double links. And then quiz 5 is out there, of course, and will span all the way till lecture 20. And that will cover our hash tables. And then we'll have 2 labs this week. Pretty quick lab today for symbol tables. And then we'll have a special hashing lab, something called the DJB hash. You can look that up if you like, if you're interested. But we'll go over that in class more or less on Thursday. So any questions on the midterm or the grading or the process on that at this point? Yes.
I know like a few teachers do this, but do you give like A pluses in your class?
I'm a strictly numbers kind of person, so I will, if you max out at 100%, that maps to what the College of Marin A is. I don't know if that's an A plus. If it's
So
if
like a college grade.
Yeah, I'll come back to you on that. That's a fair question. I just can't remember what that maps to. It might be an A plus actually. It's whatever is standard for College of Marin. Every teacher can adopt a different grading rubric on that, but I'm pretty sure I use the standard one for all my classes. So, but yeah, let me check on that as well. Thank you for that question. Okay, so today we're going to talk about just some basic. I think everybody probably knows this about C++, but we'll just sort of reintroduce the C++ string class briefly, and then we'll kind of use that in a variety of things today. So most of the time you don't have to include it, but if you're ever having troubles getting string data types to work, make sure you pound include the string library, and things should work pretty good for you. Primarily today, we're going to start talking about key value pairs. So a key colon value is kind of just it's a common notation. It's not necessarily something we say in code, but it's a pairing of a key that allows us to find a particular value. And they often come in this pair, and many databases out there, including the one that just crashed the whole world from Amazon, the DynamoDB database, is a key value pair database. So key value pairs, even as humble as they are for our class, are incredibly common and powerful out there in the world. And we'll look at some examples of how people might use them. So a lot of times I like to think of it as this doorway that I can't really see through. It's got no windows. You come knock on the door and you ask for something, and so the thing we ask for is the key, and the package that gets delivered to us, if we have a key that matches a package, is the thing that we get back. That's what we call the value. So I found it initially to be confusing. I don't know why, but it's like, wait, what is this? Like, so if I have somebody's Moodle number, right? It's like maybe we all have an ID number for being at school. That could be our key, and the value could be like all of our grades or all of our, payment information or whatever, right? So that box could be a whole bunch of things associated with a particular key, and so we get to choose how we want to organize that data, when we're actually storing it in our database. So we're essentially asking when we provide a key, is there a box that goes with that key or is there a value that goes with that? And what we get back is, of course, the box. It's like, here's a whole bunch of information. And that box might have the key in it. Like it might have my first name, my last name, and my ID at the school. So it is possible that the value could contain a key, but usually the key is what we use to get the box in the first place. So we might get the value back. We could ask for something via another key and be told, oh, I don't have a box for that. Go away, right? And it's not like I can poke around and ask other questions. I just know that that's not here, right? So those are what we refer to as symbol tables. And symbol tables can be implemented in a lot of different ways. And so this week we'll start looking at a couple of those ways of implementing them. And homework 5 is in fact going to actually do an implementation of that. Now, that means that the symbol table itself is an abstract data type. It's an idea about how we want things to work. And we can use object-oriented design to sort of mirror that behavior through class methods and data members. And that's exactly what we're going to do. But there are kind of two types of symbol tables. Some are unordered, like we would probably never really want to list out all of the students by sorted, IDs, right? So hopefully we're all assigned IDs in a random way that prevents people from sort of poking around and guessing at what somebody else's ID is. That may not be the case, but very often when we're assigning a key that can be used to look up something, that key is very much randomized so that we actually, prevent people from hacking around. So that often results in an unordered implementation, okay? Sort of like license plates on cars. It's not totally easy to just sort of pick a license plate and guess what the next license plate someone got on the second, the plate right after that, right? Hopefully that stuff is somewhat randomized. Now, other times we do want to have our keys sorted. So if the key is by last name in a database, we might want to walk through the keys in order and print out all of this information by last name. Okay, so that might be actually a useful thing. That's going to be two different potential data structures for that. Okay, and we'll talk about what those things might be. But the unordered one that we'll explore and we'll use in our homework 5 is what we call hash tables. So where we really don't care about listing out, people by their keys in some ordered fashion. And then the other one is going to be our friend, the binary search tree or a binary search array. So that allows us to use that log base 2 searching performance in a balanced tree to go find stuff really, really quickly. But there's no point in dealing with all that infrastructure if we really don't care about order, right? So there are these other systems, hash tables or doubly linked lists that we'll look at that can give us maybe a little bit more speed with some less memory use. Okay, so we'll look at all of that over the course of the next 2 lectures and try to give you a good sense on that. But let's dive in just briefly to the C++ container for strings. This really is a class. So string is not like int or char or float or double. It's an actual instance of a class. So it's like a box. And that box is sort of like masquerading as a data type. But in truth, it really is us creating an instance of a class. And C++ allows it to sort of behave like we're saying int x. So that's like saying int x. But I'm really saying create an instance of the string class called my name and don't put anything in it just yet. But as we might know, it has all sorts of cool methods like dot size, right, that we could use. Um, and .at, which allows us to pull something out at a particular location. But most of the time, we can just sort of treat it as a simple variable and assign values to it. And that's the really nice part about doing that. Okay. So I think we've probably done a bit of that over time, but we're going to start using this data type in more and more of our code because, we want to work with words and collections of letters. Okay. So hopefully we sort of recognize the dot size is the number of things. And if we subtract one, that gives me the last position. There are other ways to get to the last character in a string if you want to dig into the other methods that these things have, but we'll tend to simplify and use that right there. We can also use the dot at instead of the square brackets. Now, why am I telling you this? Well, if you go out of bounds on a string, using the square brackets, you may or may not get a crash. And in particular, if you have a vector of things and use square brackets, you may or may not get a crash. But if you use the at, you will get an immediate crash, or what we really call an exception, which is a controlled, disassembly of our program. Like it's like, hey, I'm going to shut down now because you went out of bounds. And that's a really good thing for homework 5. So for homework 5, most of the people that stay up really, really late working on it are chasing down pointers or things that are going out of bounds. And so you are more than welcome to use these at methods instead of the square brackets in case you think you might be doing that. So it's not a big deal to go in and change it when things are looking like they're going off the tracks. Or you can just develop from the very beginning using these at methods. And the at method is true for both the vector, of course, and for the string. So it's just if you feel like you're kind of maybe a little on shaky ground, I would say go with the ats, and you'll probably benefit from those errors that will come up much sooner. Okay. Now, the other thing to be aware of about these things, and they look like normal variables, they sort of go away magically when they go out of scope. And we talk about that more in the advanced C++ class. But essentially, whenever you have a pair of curly braces with some variables inside of them, those variables are called automatic variables. And so this string variable here is kind of an automatic instance of a class. It will automatically self-destruct and clean up its own memory after it goes out of scope. And that's a really good thing as well. So we take most of these things for granted because they just sort of work all the time. But it's good to know, that these things are out there, and we can always dig deeper into that if we want to, if anybody's curious. So let's look at the symbol table idea. Where would we use this or see this used out in the real world? All sorts of places. Dictionaries, the word is a key, the definition is the value. Phone book, look up by last name, get the phone number. The web search, maybe I put in a keyword and Google search provides me a list of pages. That could be the value that's provided. All sorts of things. A URL, right? DNS servers, for those of you who know what that is, a URL is going to actually map to an IP address. So if I am, google.com, I'm going to get an IP address for that from the DNS server. So there's all sorts of examples out in the world where these key value pairs actually solve really, really nice problems. And we get to decide what the key is. It's not like there's only one way. We could have a reverse lookup, right? So sometimes I want to look up a phone number and find out somebody's last name. So that's the flip, right? That's making a key value pair where the key is the phone number and the value is the last name, right? Sometimes these are referred to as reverse searches. So we kind of do have to make a choice as to what's going to be our key. Okay. So here's the dictionary example, of course, acupuncture with a definition, acute, etc. Okay. So we may want to see the definition, or we may want to update the definition, or in other words, the value. So there are a couple different operations we might actually want to perform on that. Okay. So here's some things that we might want to do. Given an ID, find the last name. And I'll try to use this color sequence today to help us keep things associated the right way. So keys, I'll have in blue and values in purple. So given a particular zip code, I want to look up the name of the city. So I want to get the value based on the zip code. Okay. I know this seems super basic, but once we start doing it in code, it gets a little more confusing. Or maybe I want to translate a word, right? So here's a word key. Give me the translation of that in some other language. Okay. So lots and lots of examples. Now, if there is no value, and we're just sort of checking to see a collection of things, then we tend to refer to that as a set. So in coding terminology and a variety of other programming languages, if there's no value, we think of that as a set. So that's very much the case in Python and also the case in Java, I believe, in C++ as well. So if you're curious about, what goes with what, C++ and Java maps are symbol tables, and they may be a hash table or they may be a binary search tree. But if you just have a key and no value, we tend to call that a set. So we'll see some of that as we go forward. Okay. Now, whether they're sortable or not depends on whether we want them to be. It doesn't mean that just because we're using a numeric key that we have to use a binary search tree. We could choose to use a storage mechanism, an implementation that does not allow us to provide for things in ranges or minimums and maximums. Okay. But if we were interested in getting the minimum of something in the database or the maximum or a range of people whose names go from like, A to Q, well, then we need to actually have our implementation support that through comparable keys. Okay. So IDs, alpha strings, you name it. We can find all sorts of ways to do that. And the underlying implementation is going to be one of these things we've already studied, binary search trees. Okay. Now, if they're not comparable or we don't care, that's where we're going to do this hash table thing. And we'll describe more of what that hash thing is on Friday. Many of you probably heard the word hash and associate with cryptography or encryption, and they are pretty much related. So we'll dig into that on Thursday when we get to lecture 18. Okay. So in my notation, I'll use that colon, but not everybody really kind of uses that, and we won't necessarily see it in code exactly the same way. Okay. But a lot of these cloud-based things like the DynamoDB associated with the Amazon problem this week is key value storage. So you're going to give them a key, you're going to give it a value, and you're going to come back later and say, hey, I got to update that value. So whenever you log into Facebook, right, your key is maybe your email and your value is everything associated with your Facebook account or whatever. I'm probably not dating myself by using Facebook as an example there, but that's exactly the association there. So a lot of these key value pair storage systems are in the cloud, but we can do it in memory using these tables and simulate the kinds of things that are being done outside in the ether sphere today. Okay. So things you might say to a symbol table: do you have key 314688703? Right. So that's like given a key value, in this case, a social security number, and asking for an associated key, right? And it might come back with, yes, that would be Jeff Yates. That's not my social security number, but just in case. Or, hey, is absquatulate a real word? Yes or no, right? Look that up if you're playing Scrabble and give me a true or give me the definition, right? Another way that we can use symbol tables is for histograms. So how many times have I encountered the word banana? So the key is banana. The value that we want to update is the number of times we've seen it. So maybe every time I encounter a word in a book or something, then I might increment a counter that starts at 0 and just goes up. And that way, every time we encounter a word, we just go update its value by incrementing by 1. And now we have a nice little histogram. Okay. So lots of ways to actually do that. And we may want to remove not only the key, but when you get rid of a key, you get rid of the value associated with it as well. So you're not always going to just have a key, you're going to have a key and a value. And so both of those things need to go at the same time. Okay. So we're going to go ahead and implement all of this in homework 4, or homework 5 rather. So, and we're going to use a combination of hashing and linked list to do that. Okay. So let's take a look at our abstract data type that we're going to use, and it's really not very complicated. Here's just a little more symbolic information for you with regards to duplicates. So this idea of a symbol table exists kind of between the user of the database and the cloud, let's say. So I show up and I have an email, biff@gmail.com, and a value of 25. And I want to insert that key value pair into the symbol table. Okay. So what we have to do is sort of find out if Biff is already in there and potentially, sort of update the value associated with Biff if we're not supporting duplicates. Okay. So, and then later on, I can say, hey, what's the value associated with that particular key? And I should get that value back. Okay. If I update that key that exists, it should overwrite the ID value if we don't support duplicates. And that's a big question, because if we don't support duplicates, that means I have to search the entire database somehow to make sure that I don't have a biff@gmail.com before I add it, because I'm either going to have to insert a new key or update an existing one. So that's a pretty big decision right there. Like, do we want to allow duplicates in our symbol table or not? Okay. So that changes how we have to insert things. Okay. So that's our insertion and our get value associated. We give it a key to get the value. We give both the key and the value to actually add a new pair. And we can't really search by value. So we can't say get 37 because symbol tables don't do that. If this is 37 is the value, they're really not built to do that. You could just do a brute force linear search through it, but that's not really what they're built for. So our abstract data type is not really intended to be used in that particular way. Okay. We give it a key, we always get a value. Okay. So those could be anything. So here's some code or some methods. So insert key val, right? Overrides the prior value, if any, or inserts it into the tree. Delete key, deletes the key and value. We don't obviously need to say what the value is to delete it because it's associated with the key. Okay. And then just get the value based on a key. Check if it contains a key, see if the table is empty, how many things are in the table, all of that pretty generic stuff. So you'll be implementing all of these in your homework 5, essentially using one of the methods that we're going to kind of summarize here. Okay. So still, that's kind of abstract. We haven't really talked about implementation, but let's look at one possible implementation, brute force. We could just say, okay, kind of like homework 3, we'll just kind of create a linked list like our max priority queue, and we'll just dump stuff in there, right? So we'll have this symbol table object, and then we'll have some nodes with next pointers, and we'll just link them together. And every time we need to do some maintenance on that, we'll go searching and we'll do some surgery on the linked list. And we kind of did this with our max priority queue before. Okay. But if we want to take it up a notch, we're going to add next and previous pointers, which makes it a little easier to pull stuff in and out and makes it a little easier maybe to search for things, but it adds a little trickiness to our code. So we do have to kind of consider all of the implications of removing something. So if I have a doubly linked list like this, right, and I want to do something to it, I kind of got to be really much more careful in my code to avoid crashes. And this is where the monsters lie in homework 5. So in homework 5, when you start editing these doubly linked lists, which you will be doing, the code that we're going to go through today will help you because it's very carefully crafted. You can of course, you can create your own code, but be cautious here when you go through these things because they're just fraught with peril. So let's look at our updated node structure. We have a previous pointer and a next pointer. Start out as null. We have a key and a value. Okay. So our key has got nothing in it. It's a string of 0 size. So if you know that the size of that thing is 0, you know that there's nothing in that node yet. Okay. But we got to put some value in the value, and it could be anything we want. But our constructor is where we're really going to initialize those things. Somebody gives us a key and a value for a new node, and we pop those things into these data members here. Remember that the orange ones are just local argument values, so they go away after we're done constructing. So these are the things that are really important. Okay. So that's what we're doing inside of our node structure there. So that's our node, okay? And previous is going to be our kind of addition. So if I want to create a new node now, I just say new node, some string, and we're going to be working with words basically. So some string and then some value that's associated with that. And now new node is a pointer. So I can say new node arrow key to get the key, or new node arrow value to get the value. Okay, so hopefully that stuff is somewhat familiar because we did some of that previously in our homework 3. Okay, so that's kind of our node. Now our symbol table class, we're going to keep track of the size of our simple linked list symbol table. We're going to have a head pointer, and we're going to have a find key method, and we'll probably add more stuff over time. But here's kind of where we're starting with our symbol table class. Okay, so we create a symbol table with a null head pointer and a count of 0, and we'll then insert or find keys with that in a variety of ways. Okay, so there's our insert, print, delete, etc. So we're going to go through this today, look at the code, and although it's a little bit dry, it's useful for your homework 5. So hang in there as we go through this. So if I wanted to just create a symbol table called ST, I could do it that way. I could just say symbol table ST, and that creates this whole bubble of stuff with current size 0 and no head. Okay, and I could say st print me, right, if I had a print me method. So no arrow here because there's not a new. I'm in C++ saying create a instance right here, right now, and then I will use the dot to access the methods or the public attributes inside of that class. So this is a little different than what we were seeing with the node before. We're saying node pointer arrow print me, for example. Here we're saying st dot, okay? So that's because we just said int x here, essentially. Data type followed by the actual variable name, okay? So I'll help you with this syntax. This is very C++. Because C++ supports pointers and instances, we have to deal with both kinds of notation here, okay? So, but that is how we do that. And I could say st.insert key value foo, for example, and that's calling the method for my symbol table, right? Which we haven't really seen yet, but it's going to be that one right there. Okay, so this is what we'd see in our main section of our program, basically. Okay. So let's take a look at our find key method. So if someone is looking for a key string in our symbol table, we're going to do some searching. So here's where the pointers come in. I say, okay, I'm going to grab the head pointer, and this is all inside of the symbol table class. So this is the find key method inside of my symbol table class, which means that it has access to the head and the current size. Okay. So you got to kind of imagine we're building out this code right here on the next slide, okay? So let's go back there. So we're inside of that class and we say, okay, I'm just going to grab the head, and while the temp is not null, I'm going to be looping, right? And if the temp arrow key is equal to what I'm looking for, then just return the pointer, because that's what we need to return from the function. So find key is really just trying to find a pointer to the key, not really the key, because we already know what the key is, right? So we want to find a pointer to the node that contains the key and the value. That's really what we're doing here. And inside of that loop, of course, we have to say temp equals temp next, sort of going down that linked list of things. So if I get past that loop, that means I never found it, and I have to return a null pointer. Okay. So this is just basic blocking and tackling. I'm just searching down a while list, trying to find a node that has the key. Otherwise, I'm going to return a null pointer. Okay. So this is all kind of written for you. You don't need to worry about that part too much. But we're going to use this for all of our other operations inside of our symbol table. Because the first thing we got to do is find a thing or not find it in order to know what we got to do next. Okay. So if we do find it, we can say found key, arrow, previous, and previous would be the parent of that. So I have no way of knowing where that thing got found. It might be in the middle of a linked list. So this might be my found key, and it might be like pointing to this, and the thing is pointing to that, right? And it's deep, deep, deep in some linked list, and it might have more things coming after it. So we don't know where that found thing is coming from, right? So just keep that in mind. Even if we found it, then we got to do some other thinking. So with that in mind, let's take a look at some of the primary operations. And all of these things are things you're going to ultimately end up using in some way in your homework file. So let's take a look at the insert operation for a doubly linked list. So we've got a head pointer and we've got something that we want to insert. And let's say it's an existing key. So if it turns out that it's an existing key, it's kind of our easiest situation. We just have to find node, right? So found key equals find or find key foo. And then all we got to do is update its value with 1, right? So we say found node arrow value equals 1. So I'm finding this, updating with that, and I'm all done. That's really an insert with an update, okay? And probably we want to return some hint as to, yes, I did update it, or no, I didn't, okay? So maybe the return value of true means, yes, I updated it, and false means I just inserted a new one, right? It doesn't matter. We could choose it the other way around, but we kind of want to know, was it there already or was it not there already, okay? So we'll see a little bit of code around that here in just a minute. But let's take a look at the new key example. So I'm going to try to insert foo. Obviously, foo is not here. So question, do we want to do an ordered list, or do I just want to put it in at the head and, be, lazy, technical term, lazy insertion. So let's do the lazy insertion. Let's just put it at the head. Okay. So we kind of know that, right? So if the find key of that thing is null, then we're going to create a brand new head, right? So that's the code that produces that thing right there. And then we got to hook it up. So we can do it a couple ways, but we want the head to point to new head, okay? And we need the head's previous pointer. Maybe the first thing we got to do is say head previous should be pointing at new head, okay? So head previous equals new head is just that hookup of the dotted arrow, right? And then I kind of got to get the new head next pointing at head. Okay, so new head next equals head, right? And then I finally update the head at the very last minute, okay? And now I've got that thing inserted with all the pointers kind of fixed up, okay? So insertion at the head is not too bad, okay? If you know it's at the head, okay? Which is essentially, what find does for us, right? So we know we didn't find it, so we'll just put it at the head. Okay. And we're not doing anything in order here. Okay. So let's see if we can do this one real quick in code, right? I'll see if I can do it without goofing it up. Always a little more challenging doing it on camera, but makes it exciting. All right, so let me get us fixed. You can go just search for to do if you're following along. So I can just say control find TODO. Okay. So let's get rid of this guy here. So we're looking for key, and we want to update it with value or insert the key. So if the found node does not exist, right? So in other words, if found node is equal to null pointer, okay, then we are going to, or not equal to null pointer, then we're going to overwrite a particular key with a particular value, okay? So we're just going to say found node, arrow, value gets val, okay? So this overwrites the value per attribute. And then we're going to return true, indicating that, yes, we did find an existing node. So that's just a convention that I've set up here. And it's just a nice to have. Just lets us know what actually happened. Okay? Otherwise, if we get this far, that means, well, we didn't find it. So let's create a new one. Let's point the head. So let's try, see if we can get this. Point the head at the, point the new node at the current head. So we'll say new node, arrow next, gets head. Okay. And then we'll point the old head at the new head if the old head was not null. Okay. So this is a tricky bit. So if head is not equal to null PTR, then we want to point the new head, point the old head. So we'll say head equals new head. Okay, point the old head at the new head if the old node, point the old head at the new head if the old node was not null. Okay, so if head is not equal to null, so let's think about that. Head is not equal to null, then head equals new head. Okay, so we're updating that already. Update the head to point to the new head node. Wait, I'm misreading that. Point the old head at the new, oh, I think what I mean there is if head, point the old head at the new head. I'm going to cheat, actually. Sorry, guys, this is where I go. If the found node is not, oh, sorry, here we go. If the if the head is not equal to null, head prev equals new head. So that's what I meant. Head, there you go. Prev. I think my comments are not clear here. So if head is not equal to null, then head prev gets new head, right? Because we could have an empty linked list, right? So trying to use a previous pointer on a null head would have crashed our program. So we got to do that little check. A lot of us will crash on this one. So this one is kind of important. So we have that back pointer updated. Now we can update the head to point to the new head. Okay. So we'll say head equals new head. Okay. And we will return false, meaning we did not update an existing node. Okay. Okay. So that will handle that. Okay. So let's see if I actually got that right. Okay. I have a small typo. I think one of my comments, new head, new node could be head, point to new node next. New, is it new node? Okay. Okay. New head, sorry. Okay, this is the challenge. There we go. Okay, so now, and this is good to just practice this at least one time because this is how this is going to work on the input side. So if I add a key string of 1 and a value of 1 to correspond with that, now we can kind of see there's our key value pair, right? And we'll just keep going. So I'll just say 2 and then a 2. You might need to scroll down, right? And now we've got, you can kind of see it getting inserted at the head there. Now this code that I write will test the forward and backward links by walking all the way through the linked list in one direction and then walking back the other. So this is a utility function that I've written, and it'll be part of your homework set that will test your links. And if there's a corruption, you'll find out pretty quick because it will either go in an infinite loop and crash, or it will, it'll assert and tell you got to kind of check things. But if I want to update the 2, for example, to have it have a value of 200, I should be able to do that, and it shouldn't create a duplicate. That's going to be the other thing that we want to make sure we're doing correctly in homework 5. Okay. So we're going to generally not support duplicates for homework 5. Okay. Okay. So that's our insert key. We'll take a look at some of these other ones. I might not live code all of them because I might end up just butchering it for you, but let's take a look at some of the other major operations. So delete key, we've got a couple different cases. So first off, if the key doesn't exist, obviously we can't delete. So if the found node is null, right, after searching through everything with a while loop, then we got to return some indication that it's, that we couldn't delete it. So we'll just return a false in that case. Okay. Well, that one's pretty easy. Okay. If it's at the head, we have to delete it. So how do we know it's at the head? Well, if the head pointer and the found pointer are the same, then we know it's at the head. Or if the found pointer previous pointer is null, then we know it's at the head, assuming we haven't broken any of our code so far. Okay. So either of those tests can work for you. Okay. So in order to delete that thing, we want to push the head pointer to found next. Okay. But you could also say head equals head next. That would be the same piece of code. So head equals head next or head equals found node next should do that for you. Then, this is perhaps the slightly trickier part. I want to go through from the found pointer, come back and nullify the yellow pointer here. So I'm saying found node next previous gets null. Okay, so I have a little animation for you. So I'm saying found node next previous gets null. Okay, and then I delete that thing as a last step. And I have to do it in that order. I can't delete it before I follow its pointer. I could say head previous gets null after I update the head. That would work too. And I might have a little animation that shows that. Yeah, so I could do that. Head gets found node next. Head previous gets null, delete found node. And then, return true because we found and deleted it. Okay. Let me just go back and show you that before the final thing there. Okay. So, okay. Questions on that part? Okay. All right. So that's case number 2, right? That's finding at the head. Okay. So let's deal with finding at the end. So if we found node is here, and this is where we get a benefit from our back pointers. Instead of having to do that kooky thing we had to do in homework 3, where we kind of stop one before the caboose, here it's just oh, I'll just use the previous pointer. So I'll just say, hey, if I'm at the end, I will say found previous next gets null. Okay. So found previous next gets null, and then delete found node. So that's pretty crucial. Very often we forget to nullify the next pointer when we delete. And if we forget to do that, next time we print, we're going to walk off the end and crash our program. So we got to obviously delete that thing. And most of us dealt with that in homework 3. Okay. But that back pointer really helps us, or that previous pointer. We can say, hey, found previous next gets null. Okay. So that's a cool trick. Okay. And then delete. So that's our third case. There's one more, and it's probably the most elegant one, but the code might seem a little funny. If that's our found node, we got to wire around it. So I love this one, really. So keep in mind that this is our found next, right? And this is our found previous. So if I say found previous next, right? So found previous next is pointing to this thing equals found next. I'm wiring around that found node, okay? So found previous next equals found next, which is pointing over here. That's what that's doing right there, okay? So we got one of them done. And then the other one is just the reverse. Found next previous, right? Found next previous should be set to found previous. So that wires around there. And now we're ready to delete that thing in the middle and everybody's happy again. Okay. So those are our 4 cases. And it's really important, especially when you're dealing with linked lists, to break things down into cases. And the order in which you do them is important. So if you try to tackle the middle first, you're going to need some additional code to tell when you're in the middle. But if you look at the order in which I did it, where we said, okay, null first, then head, then tail, if we get this far, then we kind of know we're dealing with the middle, okay? So you could create about 12 cases for this if you really wanted to, but you really only need 4, okay? So if you find yourself with a really long pile of code dealing with a lot of this, maybe take a step back and think about that, okay? So let's just take a look at the code real quick. I'm not going to live code this for you, but let's just kind of take a look at where the blanks are, and then I'll pull up the solution code here in a second. I know this is there because I tested it before. Come on, there it is. Okay, so I'll search for to do, TODO. Okay, so if the key was not found, right, just return false. So that one's pretty easy. That's our case 1. Otherwise, if the found node is the same as the head, right, then head equals found node next, right, or head equals head next. So that's all of the code that we were just looking at. If the found node previous is equal to null, not equal to null, then if found node next. So this is an important thing. If I'm going to check found node next, I better be sure that found node next is not null, right? Because if I try to follow that pointer and this is null, I'm going to crash. So if you're ever wondering, like, what is that doing? That's just making sure it's safe to step off of this rock and step onto that one, right? So if found next previous is equal to null, the previous pointer of the new head, right? That's the previous pointer of the new head. Then we can delete the found node. Okay. So let me switch over to the solution code just so you can see this and I don't trip all over myself doing it live. But there's our case number 1. Okay. Here's our case number 2. If the head is equal to found node, then head equals found node next. If found node next is not equal to null pointer, then found node next previous equals null pointer. So we're basically saying follow that next through, hook back, and set that thing to null. Okay, and then you can delete the found node. Okay. And you can go back and look at the animation of what we did before. You'll kind of see that they line up with the code here, right? That's case 2, case 3 at the end. So just a little bit different. If the found node next equal null, we're at the end, right? And so we'll say found previous next equals null, delete the found node. Otherwise, we're in the middle. Notice there's not even an else here because we already returned from our previous cases. That's another nice simplification. You don't have to have an else down here, but you could. That could be your final else that would trigger. But the code for that is now a lot simpler because we eliminated the major cases before we got to that middle piece. Okay. So that's kind of my favorite way to write that piece of code because it keeps things relatively simple. Okay. Any questions on the syntax? Okay. So that's our delete. So we kind of got the hardest one out of the way. So let's look at get value, which should be pretty straightforward. So get value for foo is just about searching for foo and then returning value. So we need a while loop to search until and if we find the node. And then we just say, okay, If found node is not equal to null, just return found node arrow value. Just that simple. Okay. So that one's really not too bad. If found node is null, well, then we can't really return a value. So it poses a little bit of a problem. So in some languages, Python, Java, C++, when you try to get a value that's not there, it's not sure what to do. It actually might crash. So, and you think, why does this library crash whenever I just try to get something that's not there? Well, the question is, if it's not there, what should it give you back? It can't give you an integer back, right? So what should it give you? Should it give you an exception, something we have to handle, or should it give you some special value? So Python will give you none maybe in those particular cases, but Java and C++ might actually assert or have not assert, but have an exception that would cause your program to crash. So it's a little problem we have to think about, but we will take a cheat and we'll return a -1 just to fill the void. We have to return something at the end of our function there. That's a requirement by C++. Okay. So take a look at the code for that one. Feel free to jump in, but here's the solution for that. Okay, so get value, right? Find the node if you can. If the found node is not equal to null, then return it. Otherwise, return -1, right? So we have to return an integer in C++. We can't get away with not returning an integer. So you can return like -9999999 or something like that. But usually that poses a small question: is what's the right thing to do there? Okay. We'll come back to that a little bit later, but that's our solution. So what's the analysis for this? Just real quick, it's relatively obvious. If we need to search for something, our worst case after n inserts is going to be n, right? We got to search n times to find something. If I want to insert something with no duplicates, then my insertion cost is going to be n, because I have to make sure I don't need to update an existing item, right? So unordered, no duplicates is an important characteristic we have to be aware of. It's like, oh yeah, that's going to cost me n things because I'm always going to have to look. Okay. Now, 50-50 chance we will end up with random insertions about halfway through if we're looking for something. Okay. And then average, we're probably going to end up with n for our insert as well. Okay. Assuming we don't have duplicates. So that's not always going to be the case, but sometimes that's exactly what we want, right? If you have unique IDs, we never, ever, ever want to have two people with the same, Moodle number at the school, or the same address on a street or something. Okay. So we have to check all the values to do that. So relatively straightforward. So kind of interview questions. So these are just like, oh yeah, they're obvious, but when someone's asking you, an interview, it's maybe a little bit daunting. So let's just practice that. If you build a symbol table using a doubly linked list of unordered nodes where duplicate entries are not allowed, what is the best case performance we can expect when inserting a new node? Kind of just saw that, right? The best case performance is going to be n, right? We got to kind of look all the way to the end before we can insert anything. Did I say best case or worst case? The best case performance is not big O. So I should have used actually big omega there. So sorry about that. But we are going to have to search through everything in order to do that insertion. So let me make myself a note there. That should be big omega. Okay. Can't really draw an omega very well, but big omega is best case performance. Okay. So sorry about that. So that is kind of one question. Another one might be, if you build a symbol table where duplicate entries are allowed, right? What is the best case performance we can expect when inserting a new node? In that case, we're just going to insert at the head, right? We don't need to go searching. We're going to end up with a duplicate key. So two keys maybe with the same key, but different values. So that is also going to be a big omega. So big omega is what we say when we talk about best case. So fixed number 2 for me, right? So that can go in at the head if we want, or anywhere we want. Now, ordered operations, in other words, we want to maintain order. That's going to be a slightly different situation. So in a symbol table that supports that, we may have some extra methods, like we might ask for, hey, what's the minimum key in the database? Or what's the maximum key? Or what's the rank or select 3? What's in position 3? Or what's the ceiling? Or what's the floor? So these probably seem familiar because these are binary search tree operations. So for those of you who recall the midterm, we had rank and ceiling and all those things. One of the reasons I like to highlight that is because when we work with libraries in C++ and Java and other languages, we see symbol tables that support these things. And it's like, huh, that seems familiar. Well, that's because those symbol tables are implemented with a binary search tree underneath the abstract data type. So the API, or application programming interface, is another term that people tend to use, is really reflecting the underlying architecture. It's like, oh, yeah, this is a binary search tree underneath all that stuff, right? And so although we won't go build that literally, we can kind of get a sense that that's probably what's going on. So we would see these methods in a library that allows us to ask questions about ranges or comparative things where we are concerned about the keys that are largest, smallest, etc. Okay, and it probably is going to be something like a binary search tree underneath. So we can find it, we can delete it, do a variety of different things there. Grab a range of things. So give me back everything between this and this, right? Even if there's not an exact match at either end of that spectrum. So that's just sort of an FYI. Those are our binary search tree implementations of a symbol table, of an underlying symbol table. So you might notice that or may have seen that, okay? So the nice thing about this is, we're going to find the place where these things should go. So we have a slight extra cost. We have to go find the insertion place. But because of these double pointers, it's a whole lot easier to kind of plug something in, okay? So if we find the place where we've gone one too far, it's easy to go backwards to get to this one and hook all that stuff up, okay? So we have these methods called find key, right? That gets me the node, right? Get value will actually get me the value from that particular key. Okay. Now, we don't have to use a binary search tree. We could try to maintain an array that everything is ordered, and then we can use our binary divide and conquer when we're searching for a key, okay? So if you think back to the beginning of the semester, I think we did a lab where we just said, hey, let's divide and conquer, find something in this range, right? So that's really all we're saying here. But what we need to do is store these two things in separate arrays. So we have our keys in one array and our corresponding values in another array. So that essentially what we do is we just sort of search for the key first. And once we find the key in a particular location, we know where the value is going to be, okay? So if you're looking for A7 or anything really, we just start in the middle. We look to, is it less than an E? Yeah, let's go with the A7. Is A less than E? Yes. So it's not always going to be in the first position, but in this case it is. So we just keep dividing and conquering until we find the A, and then we jump over to the value side to pull out the value from that same position, okay? So pretty low tech, but we still get our log base 2 search speed, which is nice. The problem is, of course, if we want to add something to it, right, by inserting, we're back to that old fashioned needing to, copy everything over to a new array that's either one size bigger, or if you recall, we said we might want to double the array size so we're not copying things all the time. So we can do it. We can do it with arrays, but it's just sort of expensive if we're doing a lot of insertion operations. Okay, so yeah, not very common as a solution. Okay, so worst case, we're going to end up copying twice the data, one for the keys, one for the arrays every time, which is not what we want to do. Okay, but we can do it if we want to. Okay? So and that's, that's the slow way. We could double the size on those things. So if we go to double size and then we slide it over, then, we save ourselves a little bit of cost, but we're still kind of spending a lot of time copying data around. So it's not a great solution. Okay. Now our lab today, just to keep the code simple, will be using binary search arrays. So it's just binary from the standpoint of your search is going to be a binary search, a divide and conquer search. But otherwise, it's going to be sorted by key, and you'll have to go find the associated value with that. Okay, so that's a little peek at what we're going to do with our lab. Questions on the approach there? So we could create a node, right? So some of you might have recognized I could have an array of instances of a node where it has the key and the value stored in the array itself, right? Or you could have a pointer to a node stored in each one of these positions, right? So there's a lot of different ways in which we could shuffle this approach, but this is probably the simplest one that doesn't require you to use any pointers for this. We'll just kind of run through that real quick. We're not going to code this up, but it's got all these methods in here, so you can kind of see it actually works, right? So let's just do that real quick because we don't have to do any coding for that. Okay, so I'm just going to run it. So we'll say enter a key, string, and then an integer separated by a space, and then hit return. So to delete a key and the letter, enter the key and an X to delete it. So this is a fully functioning binary search array. So we'll say 1 space 1. Okay. And then I'll say 2, 2 space 2. Right. 3 space 3. That. And then I'm going to say 3X. Okay. So I want to delete the 3 from there. Okay. And now we got our 1 and 2. So that's pretty nice, right? So all of that is really happening pretty straightforward using a node in this case. And I think we're just doing, a dynamic array inside of here with keys and values. So I don't even think we're using the node in this particular case. I don't know why I have that node in there. I think we're just using these keys and values. Okay. Which are strings and integers. So the node, I'm pretty sure, is not being used. Okay. And there's our find key, which is just our divide and conquer game that we played, way back in the beginning of the semester. It's like, okay, what's my high and low? As long as it's, less than that, divide that midpoint and find the midpoint, check the comparisons, and then loop around, do it again. Okay. So we can do it if we really want to with arrays, and it's all good until we got to do the insert, and then it's just a little bit messy. Okay. Now we can do a recursive version of that too. We did this together in class. We did two kinds. We did a looping one, and we could just do the same old recursive one. So we don't have to use the array, the while loop. We could do the recursive version of that as well. Okay. So all of that is kind of what we just looked at working in code. So if we look at this, just comparing these two relatively unsophisticated implementations, we've got, kind of order n, worst case search and insert. We can get a log base to n search, right, for searching if we use our binary divide and conquer, but we're still going to pay something along the scale of linear for that insertion. Okay. So, and the benefit is, of course, we can pull out ranges of things if we want. We can say compare less than, equal to, etc. Okay. So this is okay for relatively static symbol tables, but not if we're doing a lot of insertions, okay? Because insertions are going to be expensive if we have to copy the array data around, okay? So that's, better, but not perfect, okay? A couple more just to think about. If you build a symbol table using a binary search array of ordered nodes where duplicate entries are not allowed, okay? What is the worst case performance we can expect when finding a new node, right? So, hey, do you have a particular thing? Okay. So if it's a binary search array, we should be able to get log base to worst case performance. So we know we're bounded by that divide and conquer limitation. Okay. So that's pretty good. Okay. Because we have everything already ordered. So it's already in order. Okay. So we're guaranteed that we can get it worst case by that. We might do better than that, but that's our worst case. Another one, if you build a symbol table using binary search where duplicate entries are allowed, okay, so we're searching what is the best case we can expect when finding a new node, okay? So if we're finding a new node, we could get lucky and find it on the first search, right? That's entirely possible. So this is a different question than the previous one. So I'm throwing different questions at you. This is the best case performance. And again, I should have changed this to omega to be proper. So I'm going to go back and update my notes because best case is omega, not fig O. Okay. And that's just because we might actually find it on our first guess. So these are slightly trick questions, I suppose. Okay. So not a whole lot more here. We're not going to dig too deep into this, but just consider that we could have a whole linked list structure, or not linked list, but our linked node structure that we saw, not arrays, but actual proper binary search trees with the AVL tree and balancing and all of that good stuff. And that is pretty much exactly what modern software libraries do. So if you have a symbol table that supports ordered operations, it's probably a binary tree, an implementation, and either an AVL or a red-black tree or some of those kind of variations, okay? And we've seen that, of course. The only difference is our node now has a value and a key, right? So we search, we find the key, and we return the value, right? So we return it up the chain recursively, probably, okay? Through some recursive search. And we won't take you through that stuff. You guys have seen enough of that for one lifetime, maybe. But you kind of know what you get with a binary search tree. Okay. And rebalancing gives us that pretty much consistent log base 2 performance, okay, even when we're doing insert and delete. So there's our kind of full analysis. And this right here is kind of beyond the scope of this class, but on average with random insertions, we kind of do on the scale of log-based n times this funky constant right here, 1.39. So we won't try to go through why that's the case, but it's still in the neighborhood of log, okay? And something you might encounter if you kind of go on to do more advanced algorithms classes, okay? So if we're dealing with a lot of dynamic insertions and we want them ordered, probably it's going to be a binary search tree. Okay. Interview question, which data structure would have the best worst case performance? So this is kind of really, it's like, if you had to choose the best thing, so your worst day ever, you want to minimize your downside, right? So do you want a singly linked list, a doubly linked list, or an array? This is probably a fair interview question. It's like, hey, we want to build this, and we might have to search through a million different colors to find one red, green, blue pair, right? So maybe we got a node that stores red, green, and blue, and then we link a million of these things, and we got to find it, and which of these things is going to sort of be the best choice for us, okay? So if no duplicates are allowed, did we say, data structure find exact key in an unordered collection of different colors? We didn't say about duplicates. So, but essentially, if we're looking for something, we're going to have to search through and unordered through the whole thing anyway. Okay. So it's unordered. I think we said that, right? So there's really no wins there, whether it's doubly linked, singly linked, or just a simple array. Okay. In this scenario, we waste some pointers, right? So we really don't gain a lot by having a linked list, except if we're inserting. Here, we have a lot more trouble inserting, but we still have linear behavior, okay? So the least worst of these is pretty much any one of them as far as the search performance is concerned. Memory, maybe there's some different things to consider there. Okay. So without ordered data, basically, there's just no way we can get a better performance. And so it seems like we're kind of stuck with linear. So you might think, okay, well, that's as good as it gets. But so this is kind of setting us up for our next lecture. So we're kind of at the end here. So the idea is, could we think of a way where things were not ordered, where we could do better than linear? Like, does such a thing exist? Well, it turns out that yes, it does. So the better thing that exists is actually hash tables. So there is a way that we'll look at for our next lecture that is way better than linear, actually, if we don't care about pulling things out in order. In fact, we'll see that it's actually in constant time or near constant time. That means if you have 1,000 or 100,000 or 1,000,000, your insertion cost and your find cost will not go up, which is pretty darn cool. So that's a nice trick. And we can do that only if we don't care about order. Okay. And a lot of systems where we store key value pairs don't care about whether, one license plate is next to the other license plate. We just want to know whose license plate is that, for example. Okay. So that's where we're going to go next. We'll kind of leave you with that. And our lab today is really just about doing a insert or a contains key method in our, I think we're using our binary search array. Okay. So we want to implement this contains key and just test it with the code that's actually used there. And you want to use the find key function first to determine if the value exists. Okay. So let's take a look at the code here real quick, and then I'll let you guys kind of get going. I know some of you might want to work on, well, actually, you don't have anything else due tonight, but let's take a look at the code here real quick. So, so we've got high level. Okay, so we've got our node class. Okay, maybe I'll back that off just a little bit. We've got our node class. Okay, we've got our symbol table with a head. Okay, so we're kind of back to our proper symbol table implementation with a linked list. Okay. And the insert code, all this stuff is written for you based on the code that we covered in class today. Delete key is in there. So all that code is working. So it's good reference code for you. And basically, this is what you need to do down here. I think find to do. There we go. Yeah. So search for to do. Oh, it's right. It's not there. So we need to implement the contains key method down below. Okay. And I thought I set that up for you, but let me see if it's there. Delete key. Sorry if I'm jumping around. Print key. Find key. Okay, I think you just need to add it to the class. So I didn't really set up a method for you. So you have to add that and implement that. But let me know if you have any questions, and take a look in Canvas. So there's more instructions in Canvas to kind of fill in around the outsides of that. Okay, so all that stuff should be there for you. Okay, otherwise we'll see you guys on Thursday, and we'll talk about hash trees. Okay, thanks very much. Have a good week, everybody.
Have your case. Oh, no.